when I look at k equals 4. So I'm looking at these monochromatic case of 4s, which are squares with the diagonals. And n equals 17. So, how many possible colorings are there? There's 2 to the 17, choose 2. It's a big number. But, if you just randomly sample, it's easy to randomly sample a million graphs. Okay? And then I said, show me what the sample histogram looks like. That's what it looks like. It's pretty nice looking, right? It's not... It suggests that something's going on. So that's what it says to me.
Do you have a conjecture for the distribution? For the limiting?
We'll have to see.
Yeah.
Perhaps.
Yeah.
That would be amazing.
Yeah.
So, we got this. Well, first thing to check.
What did it measure again?
So the x-axis is the number of monochromatic subgraphs in the coloring. And then this is the frequency is a decimal. Okay, so first thing you want to check is a Poisson. Well, so this is squished down. This is the same graph, just squished down, so that I could fit the Poisson. And that's the best fit Poisson. That's not any. That's the MLE, if you know statistics, the maximum likelihood estimators for this gives me that. So, no, it's not Poisson. Not right here, right? Okay. But I know that the limiting distribution is Poisson. So I have something to go on. So I know that if there's a distribution, then I should be able to prove that in certain conditions the limit becomes Poisson. But that for small k, it should fit this pretty well.
So this was k equals 4?
This is k equals 4. So yeah, we're far away from infinity.
So for k equals 3, it's much easier?
K equals 3, I think you can do it completely. Yeah, I think you can actually write down what's going on. Okay, so I know this, and so you'd be surprised at how many are related to the Poisson. And you'd be surprised at how many of those well-known distributions that are Poisson related don't work. It's a lot of them that don't work. Here is a convolution of the negative binomial of Poisson. Pretty clear, so I probably don't have to say anything. I have no idea, right? So, but it is Poisson related. It's called the Delaporte distribution. And up pops this actuarial science thing that I went to undergraduate for. I didn't know about this because there's only one person who has ever used it in an actuarial claim. That's it. So this is not something that anybody knows. There were 2 papers on it. One was, this is a distribution. And the other was...
Did I put it?
What's that?
Did I put the paper?
No.
So who
I don't know
named
why it was called that.
Somebody named it.
Somebody named it that.
And did I put the person's name?
That's my guess.
Yes.
I don't really know.
Yeah.
Because there's really not much at all on this.
So there's no Wikipedia entry on the Delaporte?
There actually is. I'm surprised, but they're statisticians, so I'm not surprised. So, yeah, you can go to the Delaporte distribution. Here's the moments. Here's the kurtosis, skewness. It's all there, so that's very helpful, right? But it's not linked to Poisson related, so I had to dig. Now, I want to first show that it does have this asymptotic Poisson property. But not always. So if I let D be Delaporte, so it's got those 3 parameters, Poisson only has 1, so I'm telling you this is how you combine it. And if alpha looks like that, and beta looks like that, and n is little o of this is an interesting number though. So if you know Ramsey theory, this k to the 2 to the k over 2, I'm allowed to be a little bit bigger, and it works, but not much bigger. So that may suggest something. I need that n so that alpha beta goes to 0. That's where it's used. But I first want to attempt to justify these. So obviously I just didn't pick those out and say, let's see if these work. So I've got these. Where are they coming from? Okay, so I know the first moments. Doron wrote something, symbolic moment calculus 2, where he has a maple program which calculates other moments. So I went through and tabulated these. Now these are the leading terms. His will do plus a whole bunch of other stuff, but they're all lower term in it. Okay, and so you look at this and you say, wow, it's a really nice pattern. So these are going up by 1, these are going up by 2, and then I've got something going on with the powers of 2, but everything else seems pretty controlled. Well, that's where those alpha and beta are coming from. So if you come through here, then alpha beta squared is coming from the second moment, and then alpha beta cubed is coming from the third moment, and then you look through these and out pops this alpha and beta. And so this Delaport says, well, you know, this isn't a proof, but this is pretty strong evidence that I have my alpha and beta are following that. Really looks like that. And then if my n is kind of asymptotic what people think the Ramsey number is, then I can show that asymptotically, let's see, it goes to Poisson. So it's a convolution. So generating functions, I can just multiply them. And so the top one is negative binomial. This is that right? Poisson. This is negative binomial Poisson. And then here you have this 1 minus, now alpha is going to be going to 0. So I'll write it like this, and then I need some, this alpha beta is also going to 0. But then, I know you hate this, but I need something on t in order for this to work. But I will justify it in that moment generating functions are not the same as generating functions. They're not placeholders because you use derivatives in order to find the moments. So if I have that, and you'll see this is a very small radius, but then the moment generating converges to Poisson. And so you do have, since and moment generating functions are one-to-one with the random variables. So I have that this goes to Poisson. Okay, great, but you didn't show me if it's any good. Okay, it goes to Poisson, could be terrible. Okay, so does it do better than Poisson? Let's see. You can decide. Blue is Poisson. Red is the Delaport with maximum likelihood estimate. That is not tracing it. That is a separate. Plug in the formula. That's what you get. That amazed me.
So you have at least an empirical proof that this distribution is Delaport.
Sure, you want more? There's n equals 18 with k equals 4. There's n equals 19, k equals 4. Here is n equals 45, k equals 5. And you'll see there's some spikes at the top, right?
So now Delaport will get another citation. Thanks to your paper.
What happens is, so I wanted to know what happens to these spikes as we get more and more samples. It comes down and it matches it. The problem is that when you're getting out to here, the samples are really expensive. But we see these spikes come down.
But eventually it becomes Poisson if k is big.
And when k equals big, this distribution moves to the Poisson. So let's look at arithmetic progressions. Right? I had so much success there. Let's see what I can do here. Same approach. So I want to look at the distribution. How many arithmetic progressions? So this one's easier to count. You can go much farther, but it's the same thing. So that is what came out. Number of arithmetic progressions against the frequency. looks familiar. There is the Delaport maximum likelihood estimate for arithmetic progressions. Completely separate thing. And they all look like that. So every single graph that was produced, and we have 20 or so, this is what's going on. Okay? Very good fit. So there's some more. And you look, you see that we're at 1131, 1132. And you see this spike again. And so it appears this time too. And so that begs the question, what is going on here? So we have a distribution that looks like, to me, an incredibly good approximation for it. And so now, if you assume that's the distribution, so that's a big if, so that's, in your theorem, if, not is, you can go through and calculate all of those probabilistic Ramsey numbers. You can set in a small variable, and you can find just a slew of these. So my next project is, I want to find what that alpha should be, so that when I plug it in, I get numbers that are really close to the Ramsey numbers. So where's my tolerance here? So can I do that, get a tolerance that says, really, these are pretty close. And so you can say, I almost have a formula for the Ramsey numbers. And so that's...
So if nothing else, if I get better bounds, like these heuristic bounds.
So you'll be able to provide heuristic bounds for anything.
Wow.
And so it's still a work in progress.
And right now, the bounds, they're not even heuristic bounds. Like for R5, it's the best.
It's the best, so you find a coloring that avoids it on one side, and then the other you have to do some kind of structure theorem to show it. Yeah. So they're not heuristic at all.
Yeah.
So if I can say, well, it's probably in this range for all of these, that's the goal. That's a pipe dream, obviously, but this kind of surprised me that it matched so well. So, since I've been chair, if you ever get to become chair, you'll realize you get to do no research from August to May. So this was done last summer. And really all I can do is, I typed it up as we were going and then I put it on this slide.
So is this written up yet?
It is half written up.
Okay.
Yeah, so all the stuff you're seeing is written in the paper. But there's a lot more that I want to do. So my question is, there's talk about this Poisson paradigm for asymptotics. Is there actually a Delaport for smaller numbers? Because that's what's going on. So there's no reason it should work for graphs and arithmetic progressions. Those two theorems can stand independently of themselves. You can't prove one from the other. And so, I don't know why, but the evidence suggests it is. And since I know that Goron hates people going over,
Also,
I kept it on the short side for
questions.
questions.
People who go under.
So are there any questions?
Yeah, I have lots of questions.
Yep.
So, so you don't have a rigorous proof, not like here, that this is the Delaport, even for K equals 4.
No, I don't have rigorous support because if I'm looking at statistics and sampling, all I can really say is that the L1 norm is incredibly small, but I can't say it's 0.
But what about the first few moments? Can you compare that?
Yeah. So with backwards.
Yeah,
I'm looking at these.
Yeah. So how far do they agree? The first few moments agree?
Oh yes, yeah. That's not an issue. Yeah.
Oh.
So I can make them.
So that's a semi-rigorous proof.
It's yes, I would say semi-rigorous. Yeah.
So how many moments can you compute?
This is kind of the max that I can go for n equals 8.
So
and going this way.
So the fourth moment is too hard?
I can probably get this many. It becomes really difficult.
So. But as far as it goes, It agrees completely.
As far as it goes, it agrees completely for the leading term.
Yeah.
And so if the
But there's
asymptotic,
nothing
it
else.
goes away. Yeah, exactly.
So that's someone goes for.
Yes,
Yeah.
yes. Yeah, so I mean, I think there's strong evidence that this is a very close approximation, but I can't say it's equal.
So thanks to the Laporte will become a household name in
I know.
10 years.
It's interesting.
Other questions? We have time for those.
This is the slide that I was going to ask about too.
Okay.
So if we fix, say, k equals 3, and then we use the alpha beta that you get there, and then you let n go to infinity.
Well,
Is this
you can't
right?
do that. So n and k have to be related. And so you're letting k go to infinity
But
and
maybe you normalize the thing so that we can mean it's 0 and the standard deviation is 1 or something.
So yeah. It's really, so let me go to this slide. This here, there's a lot going on. And so I really need to control, so inside alpha and beta and t are these n's and k's. And so I need this to happen, but if I go backwards, so this is n to the k over k to the k, but you'll see you've got n to the k minus 1, so this is n over k to the k, roughly. And you need n to be less than that, but you need it, it's funny. It's actually, in order to get this to turn into exponential, I mean, you're used to, if this is n and this is n and this is x, then I'm fine, e to the negative x. But when you have these going to 0, which is what happens with Rn and k, then you need this to go to 0, but it can't just go to 0 in any fashion. And so that's where this bound on t needs to happen. You see this is very small. But I know it only needed to include 0, because that's where the moment generating function happens. So as long as I have this and my alpha and beta, which are related to n and k, it works. But I can't, ultimately this is what happens with large k. And so with k equals 3, and if I let n go off, these are just divergent things. And so I really need the k to go large and the n kind of pushed ahead of it.
Thanks again.
Hopefully that answers it.
Yeah. Professor Robertson, we tend to answer questions in private.